Hello, everyone. I'm really excited to be here at my first ever CppCon as either an attendee or a speaker. And I hope that I can make you as excited about atomic smart pointers as I am to tell you about them. So my name's Daniel. I'm a PhD student. I like working on parallel algorithms and concurrency. And this work isn't mine and mine alone. I have to give credit to my PhD advisor, Guy Blalock, and collaborator, RAII, without whom none of this work would exist. So a quick roadmap of where we are going today. So we will start with a really quick review on smart pointers, and then we will talk about the fundamental problem that we are trying to solve, which is the concurrent memory management problem. Then we'll talk about existing solutions to the concurrent memory management problem, so atomic smart pointers, and advanced techniques like hazard pointers and read copy update. You may have seen talks on these exact topics already earlier at CppCon. If so, great. If not, I'll still provide hopefully enough background that you can still follow along too. And then we will ask the question, is it possible to combine these ideas and get the best of both worlds? So we'll talk about the trade-offs, the advantages and disadvantages of these existing techniques, and we will see if we can come up with a solution that gives us the best of both. Okay, so let's get started with a really quick review on smart pointers. So smart pointers are C++'s answer to garbage collection. Okay? We don't have a garbage collector, and we encourage, as good C++ style, avoiding the use of raw, new, and delete as much as possible. And to do that, we tell people to use smart pointers. So we have our friend Unique Pointer, which manages a resource with unique ownership, which means we can't copy it because we can only have one owner, so it's a move-only type. We have Shared Pointer, which is going to be the main focus of this talk, which allows us to manage a resource with shared ownership, and this is usually done via reference counting, by keeping track of the number of references to the object, and then deleting the object when that number hits 0. And last but not least, there's also Weak Pointer, which is like a way of keeping track of an object owned by a shared pointer without actually participating in the ownership. Now for this talk, we are mostly concerned with shared pointer, right? For shared ownership, which is implemented pretty much all the time via reference counting, okay? So that's our quick review. I said it would be quick. Now we're going to talk about the concurrent memory management problem. This is tricky stuff. So let's say we have some kind of linked data structure, like a linked list here containing A, B, and C, and along comes thread 1 who says, I'd like to read this data structure. I would like to read through this list. Okay, so it reads the first node in the list, has a look at the next pointer and says, okay, now I'm going to follow the next pointer, see where it goes, and then for whatever reason, this thread goes to sleep. Maybe it got context switched, and along comes thread 2. And thread 2 says, ooh, I'd really like to delete B right now because I don't like B. So thread 2 says, all right, I'm going to delete B using the standard algorithm for deleting from a linked list. You swing the next pointer of A over to C, right? It's effectively splicing B out from the list, and then you delete B. Okay, so thread 2 is happy because B is gone. Okay, now thread 1 is going to wake up. And unfortunately, thread 1 is not very happy because B is gone, and now bad things are going to happen. So the fundamental problem that we have to deal with in concurrent memory management is a thread may want to delete something that another thread is still reading. And this is bad, right? It causes threads to metaphorically catch fire. So how do we solve this problem? That's what we're going to talk about today in this talk. So our goals today are to talk about, first, the existing solutions that we have, like atomic shared pointers, and then advanced techniques like hazard pointers and RCU. And then we are going to look at their trade-offs, their advantages and disadvantages. And then we are going to ask the question, can we get the best of both worlds? So we're going to look at atomic shared pointer and say, geez, those look great. They're easy to use. They have a nice API, but they're kind of slow. And then we're going to look at hazard pointers and RCU and say, ooh, these are nice, they're really high performance, but they're not so easy to use. They are advanced level techniques. And in the middle, I'm going to try to convince you that we can in fact make something that is the best of both worlds, easy to use and high performance. Okay, so let's continue our journey and let's have a look at these existing memory management techniques. So the first one is atomic smart pointers, added to the standard recently in C++20 after making it through the concurrency TS. Now, what were these invented for? Well, they were invented to answer the age-old question: is shared pointer thread safe? These are actual Google autocomplete suggestions. I didn't Photoshop this. This is actually what came up when I Googled it. Well, let's see. Is it thread safe? I don't know. Let's find out. So how does shared pointer work? Well, a shared pointer points to this managed object which has an associated reference count, which says how many copies of the shared pointer there are. So right now there's 2. And now we can do things like we can copy the shared pointer S2 into another copy S3. That's going to increment the ref count because now there's 1 more copy pointing to this thing. And at the same time, maybe S1 decides I don't need this anymore, throws it away. Okay, that dropped the reference count to 2. Then thread 2 at some point says, I don't need that anymore, I'm going to drop that. Reference count goes down to 1. And then maybe thread 2 says, actually, I want a different thing. I'm going to reassign my shared pointer to point somewhere else, which also means there is now 1 less reference to this thing in the middle, and it's now gone. So the reference count hits 0 and gets deleted. Great. And everything we just did was thread safe, in fact. So the answer is yes, if this is what you mean, are shared pointers thread safe? Because the reference count is managed atomically. So all those increments and decrements are done with an atomic fetch and add instruction. So that's entirely thread safe. And note that those increments and decrements could have happened in any order. It could have been, right, that thread 1 was the person who released the last reference and then had to delete. In this case, I showed thread 2 doing it, but either would have been fine and safe. Okay, so they're thread safe, right? What if thread 3 comes along and says, oh, I'd like to join in, I'd like a copy too. I'd like to copy that shared pointer. Well, is it going to copy the shared pointer before it was assigned to other thing, after it was assigned to other thing, or, oh dear, as at the same time that it's being assigned to other thing? We don't know, and therefore this is undefined behavior again. And once again, bad things will happen. So the answer is that shared pointer is thread safe sometimes, right? It's thread safe if all you're doing is changing the reference count by locally copying your own shared pointer around, but it is not thread safe to copy a shared pointer from another thread that might be modifying it, because these things are not atomic. So what do we do? Well, C++20 came along and said, I've got a solution to that, atomic shared pointer. So this is just a specialization of stdatomic that allows you to put a shared pointer in it, and so you get the API you expect from stdatomic. You can load from it, which gives you a copy of the shared pointer. That's going to increment the reference count. You can store into it, which is also going to increment the reference count of the thing you copied into it and decrement what was there before. Or you can do a compare and swap operation, which checks, okay, is the thing in the atomic shared pointer what I think it is? If so, swap it for what I want it to be, right? Standard stuff for atomic operations. Okay, so what's the benefit of this? Well, it was invented to make concurrent memory management easier. How easy? Well, let's say I asked you, how many lines of code do you think it takes to implement a lock-free, memory-safe stack? This is the classic example for talking up atomic shared pointers. So what do you think? If you answered any more than, say, 10 lines, then maybe you'd be pleasantly surprised. If you use atomic shared pointer, you can implement a lock-free, memory-safe stack in just a handful of lines of code. It's barely any more complicated than implementing a sequential stack. The only thing that is more complicated is the need for the compare exchange loop, which is like a staple of concurrent programming. So that's great. We have ourselves a 10-line lock-free memory-safe stack. Or do we? Well, am I maybe tricking you here? I said a lock-free memory-safe stack. Is this thing lock-free? Well, I didn't see any locks in the code, right? I don't see any locks in here, so it must be lock-free, right? There's no std mutex, no std lock guard. It must be lock-free. There's no locks. But of course, we don't know what the atomic shared pointer is doing under the hood. It might be taking a lock. Well, what do we think? What have the standard library implementations done? Well, 2 out of 3 of them have shipped an atomic shared pointer. and both of them just take a lock, unfortunately. Now, the good news is a lock-free implementation is possible, and you should refer to Timur's talk to see how that is done. Okay, so we have some good news and some bad news, right? We don't have a lock-free implementation in any ship standard library, but it's possible. But there's some more bad news, unfortunately. Let's go back to Google. What are people thinking about when it comes to shared pointers? Is it thread safe? Is it slow? Well, I don't know. I don't trust random strangers on the internet to tell me the answer, so let's measure it ourselves. Okay, let's do an experiment. So I have here a 72-core machine with 1 terabyte of RAM, a average desktop computer, I guess. And we're going to implement a lock-free binary search tree with 100K keys in it. And we're just going to send all of our threads at this binary search tree. And we're going to have 99% of them just doing reads. So they're just going to be searching the tree to see if some key is there. And 1% of them are going to be doing updates. So they're going to be deleting keys and adding new ones into the tree. Okay, so to get an idea of the performance, well, we first need a baseline. So here's our baseline. How did I get this? This is just the lock-free BST that doesn't delete anything. So we're going with the concurrent memory management strategy of never delete. That's a great way to make sure that no one ever reads something that gets deleted. Not a good memory management strategy in practice, but actually not a bad way to establish a baseline of what could I expect sort of the peak performance to be of this data structure when I don't have any overhead due to my memory management. So seems reasonable. Where would we expect atomic shared pointer to be on this graph? A little bit behind the baseline, a lot behind the baseline. Oh dear, it's kind of slow. Well, I guess you might ask, what atomic shared pointer is this? Is this just a straw man atomic shared pointer that takes a global lock or something silly like that? No, bad news, this is the fastest lock-free atomic shared pointer that I know of, and I know of about 5 of them. So this one is pretty good, and it still performs like this. Is there a bug in our code? I mean, it can't be that bad, can it? Well, let's look into it. So why are they so slow? What went wrong? So here's our binary search tree, right? This is our mental model for thinking about the performance here. So what actually happens when we go to read this binary search tree when it's implemented using atomic shared pointer? Well, we go to read the root, so it increments the reference count of the root. Cool. Now we go to read X, so it increments that. Okay, now we've stopped reading the root, so we can decrement the reference count of the root, and so on and so forth. We're going to increment the reference count of Y to read that, and then we're going to increment the reference count of Z to read that, and then we're going to increment the reference count of W to read that. Okay, so what happened here? I mean, this was a read-only operation, right? We were just reading the binary search tree. But now there's all these writes all over the place. I'm incrementing reference counts and decrementing reference counts. And you might say, well, yeah, okay, writes are slower than reads on most hardware. They're not that much slower. I mean, there must be something more to it than just we're adding some writes. And it is, it's much worse than that because these aren't just any old writes. What happens when I start my traversal? I have to increment the reference count of the root. What happens when the other 99% of my 100-and-something threads are also trying to read the root? They also want to increment the reference count of the root, which means 2 terrible things are going to happen. 1, they are going to be thrashing each other's caches. Okay, we're only doing reads here, so in an ideal world, in the baseline, this tree is in the cache and they're all just reading through it at lightning speed. Now, every time someone increments the ref count, it says, no, I have to kick that out of your cache because I've just changed it. And additionally, maybe even worse, we're not just doing any old writes, we are doing an atomic increment. And every thread is trying to do an atomic increment. And they cannot happen at the same time, which means all of those threads have to serialize and do their increments one after the other, which more or less explains why we get absolutely no scaling whatsoever. Okay, so that's not so great. What can we do about it? Well, maybe there are other memory management techniques we can use instead, something more scalable. So that's what we're going to talk about now. We're going to look at the alternatives, some advanced techniques called hazard pointers and read copy update. So these two fall under a broad paradigm called deferred reclamation. And the idea broadly is quite simple. The details may be tricky, but The idea broadly is, okay, if someone is reading something and I want to delete it, well, don't. Delete it later instead, once the readers that are currently in progress have finished reading. Easier said than done, but that's the high-level idea. So what does this look like? Well, let's go back to our friends, thread 1 and thread 2. So thread 1 is looking at B, maybe it's asleep or in progress. All right, thread 2 comes along again. Boy, I'd really like to delete B right about now because it doesn't like B. So it goes and does its delete operation. It swings the next pointer from A over to C. And now it would really like to just delete B because it's been unhooked from the data structure. But it's like, oh, actually, someone else is reading and I better not delete it yet. But I can't just leak it, so I'll better delete it later. So we're just going to put a to-do list item. Okay, I'll delete this later. And at some point in the future, some thread has got to come back and delete this. Could be thread 2 or it could be a different thread, depending on the mechanism. Okay, so there are several kinds of deferred reclamation techniques, and they differ mostly in these ways, right? How do I actually do that first step? I said, if someone is reading this, then don't delete it. How do I tell whether someone is reading a particular thing? I mean, it's not like I can just go and ask the thread, hey, are you reading this? It's not super clear how we do that. There are different implementations you can use. And you can also, differ in how you choose to do the reclamation. Do you do it synchronously? Do you do it asynchronously on the same thread, on a background thread? These are all different opportunities that you can try out, and different techniques will do different ones. Now, at the library level, right, when you are using a deferred reclamation technique and you are implementing your favorite concurrent data structure, broadly, what the programmer has to do is replace their uses of delete with this fancy function called retire. So delete, of course, means delete, and we don't want to do that in a concurrent data structure because someone might be reading it. So retire says, I'm done with this thing, I've unhooked it from my data structure, please delete it. Oh, but if anyone's currently reading it, just hold off for a minute. So retire broadly means delete this once any existing readers are done with it. And the usage of this turns out to be extremely subtle. I mean, we teach people to avoid raw, new, and delete because delete is quite tricky. You can double delete, that's bad. You can forget to delete. You can read something after you delete it. All of those bugs can happen with retire, and even more worse ones because now we're in the world of concurrency. So it's very subtle, and it's very easy to get this stuff wrong. It's a very expert level technique. So let's have a look now. This is overall deferred reclamation. Let's have a look at a particular brand of deferred reclamation, which is hazard pointers. You may be familiar from this from the talk on Monday. If not, here's an overview. So we have to solve this problem of letting other threads know that we are reading something. How do we do that? Well, hazard pointers uses a technique where essentially it announces to the world that it plans to read a particular pointer at some memory location. So you can imagine there is some global bulletin board of stuff you are not allowed to delete. And when you want to read something, you go and you look at the pointer, the location of this pointer, and you write it onto this global bulletin board saying, I'm about to read this, no one delete it. Okay? And then other threads, when they want to do cleanup, when they want to go and delete things that have been retired, they have to first check whether the thing they're trying to delete is written on this global list of stuff they are not allowed to delete. And if it is, they have to defer it and try again later. Okay? So that's hazard pointers in a nutshell. I mean, there's a lot more details than that, but for the purposes of this talk, that is a high-level overview of hazard pointers. Now, this comes with some pitfalls. If you are implementing some kind of search on a data structure, say searching through a linked list or a BST, and an update comes in and modifies the data structure right as you are reading it, hazard pointers are not strong enough to protect you and allow you to keep traversing. You have to restart. You have to detect this scenario and say, right, I'm going to go back to the start of the list and try again. And this is tricky. One, programmers forget to do this sometimes, or they don't realize they have to, or they realize they have to and they do it wrong. It's very easy to mess this part up, and I will show you an example in a moment of how so. This also means hazard pointers can't be applied to every single data structure because they have to be amenable to this restarting. And there's some other subtleties, like if you need multiple hazard pointers, which you generally need if you're traversing some sort of linked data structure, you have to keep track of them and make sure that you know which ones are active and which one you can reuse at any given time. This is also subtle, also very easy to get wrong. I've seen plenty of code where people got this wrong. So this is expert level stuff. This is not the kind of stuff that I want to try and teach beginners. This is great. These are great techniques for experts, but these aren't the kinds of techniques that we can easily teach to beginners. So now that we know how hazard pointers work, let's go back to our performance model, right, our concurrent BST, and see if we can predict how this should perform compared to atomic shared pointers. Okay, so how do hazard pointers work? We want to traverse this data structure. Well, we have to announce the route to protect it and then read it. Okay, so we've written R to our global bulletin board of stuff no one is allowed to delete. So now we can read it safely. Okay, then we have to go down to X. We've got to announce that first though, make sure it's still alive. And from this point it proceeds sort of similarly to the shared pointer case, but instead of incrementing a reference count, it is announcing protection for the pointer. Okay, so we keep going down. We announce and read Y, and then we announce and read Z, and then we announce and read W. So, okay, what's the difference between this and atomic shared pointer? I mean, this was still a read-only operation, but it still had to do a bunch of writes. I mean, we still don't have a nice, pure, true read-only operation. We're still writing all over the place here. So we would expect some overhead. Question?
Yeah, is this like global bulletin board? Is this on global lock that we need? Like all threads shared? Isn't that even worse?
So the question was, what about this global bulletin board I'm talking about? Does this need like a global lock or something? It doesn't need a lock. So you can implement this in different ways. It can be implemented as like a big linked list of hazard pointers. I think that's how Folly does it, but I'm not 100% sure. If you know in advance how many hazard pointers you need, you can just have a pre-allocated array of these things, and then it's really fast because you just write into your slot in the array. So there are different ways of doing it depending on whether you know how many hazard pointers you need up front or not. But there's no locks. Definitely no locks. It's all lock-free. So what's the difference between this and the shared pointers, right? We're still writing all over the place, but we're no longer writing onto the tree itself. We're no longer incrementing those reference counts. We're writing to our own slots on this bulletin board, which means those writes aren't thrashing each other's caches because we're not thrashing this BST out of the cache every time. That's an improvement. And even better, we're not trying to all write to the same memory location, which means we don't have to serialize because we're not all trying to increment some counter. We're all writing, all of our threads are writing to different locations. Okay, so we should expect that even though there's a bunch of writes here, we have basically gotten rid of the contention. It's still going to be, we would expect slower than the baseline because we have to pay for those writes. But we should have gotten rid of the contention, and so we should now expect to see some scaling. Okay, so let's have a look now at the end of our traversal. How does it actually perform? So here is our experiment from before with our unfortunate atomic shared pointer at the bottom. Where would we expect hazard pointers to be? Well, we think it should scale, maybe have a little bit of overhead compared to the baseline, and there it is, and that's pretty good, right? It actually scales now, right? It's nice and, more performance when we add more threads. It's a little bit of overhead compared to the baseline, right? Because it still has to do these writes. It still has to announce these hazard pointers. But this is really good. We're getting much closer to the baseline already. Okay, so great performance, but like I said, this is an expert level technique. It's pretty hard to get the code right. Not something that I think that beginners we should be trying to teach to them. What are our alternatives? Well, we have one more popular deferred reclamation technique, and that is RCU, read, copy, update. So how does it differ from hazard pointers? Well, remember, hazard pointers work by announcing particular memory locations that they want to read. They say, I'm going to read this variable, don't delete it. RCU takes a more broad brush, coarse-grained approach. It says, all right, I'm going to read the data structure. I'm not going to tell you what. I'm just going to read something. So don't you dare delete anything that I could possibly be reading, which is possibly a lot of stuff. Even though we're only going to read some small fraction of the data structure, RCU is only going to tell us I'm reading something. Don't you dare delete anything I could possibly read, which is a lot of stuff. So retired objects, they can get cleaned up synchronously or asynchronously, depending on the implementation. So what does this mean for performance? Well, because of that coarse-grained protection that you can't delete anything I could possibly be reading, we're going to accumulate more garbage, right? We're going to have more stuff that has been deleted or that has been retired but is pending deletion because any RCU reader that is still going on says, hey, you can't delete anything that I could be reading, even though I'm probably not reading that particular thing. But in exchange for that, because we no longer have to do an announcement every time we read something, this should be faster because we don't have to do as much work in writing those announcements. So we should expect better throughput here. And another nice thing is RCU tends to be easier to use than hazard pointers because it doesn't have to deal with these tricky issues like retrying and restarting, which is nice. Okay, so there's some trade-offs here. There's some pros and cons. So let's go back to our mental model here and let's think about how do we expect this to perform. Okay, so beforehand, right, when we had hazard pointers, we needed to do an announcement for every node that we read. Now what do? A thread comes in and says, I'd like to read. So it announces, I'm beginning, I'm an RCU reader, I'm going to start reading. This tells every other thread, don't you dare delete anything I could possibly read, which at the moment is like the whole tree. But then once it's done that, what can it do? It can just blow through the data structure and read it. It can read R, read X, read Y, read Z, read W. Okay, it's found W, can release the read lock. That's pretty good, right? Like we no longer have to do an announcement that is visible to the rest of the world at every single node in the data structure. We just have to do like one announcement at the very beginning saying, hey, I'm about to read, so hold off on doing your deletions. So we should expect that the performance here, right, if we think just about throughput, again, this will result in more garbage being accumulated, but if we're just thinking about throughput for now, this should be faster than hazard pointers, right? Because now we don't need to announce at every single node. So let's have a look at our graph again, and how would we expect it to perform? Well, I mean, it's basically doing what the baseline is doing. It's just blasting through the data structure with just this one extra write. So the performance is pretty good. You basically can't see the baseline anymore. This thing is, the overhead of RCU is almost negligible in this particular experiment. So that's pretty amazing. We are trading off extra garbage, as I said, but that's pretty amazing that we have this option. Okay, so this is the state of things. Atomic shared pointer is unfortunately trailing a little bit behind in throughput, but it's oh so easy to use compared to these more advanced techniques. Wouldn't it be nice if beginners could use something as easy to use as an atomic shared pointer, but still get the throughput and performance of these things? So that's the big question for us. Can we get performance close to hazard pointers and RCU, but with a smart pointer, with something that is easy for users and beginners to use without encountering lots of bugs? So let's explore that question right now. The best of both worlds, can we get it? I hope so. So broadly, what we're trying to do is combine RAII and deferred reclamation. Okay, smart pointers are, the fancy term for them is RAII-based ownership, right? These drastically simplify memory management because the programmer doesn't have to manually free, delete, or retire things. They don't need to think about retry loops. They don't have to think about restarting these operations. They don't have to juggle their hazard pointer holders all over the place. This kind of thing is essential for non-experts, for people who don't have time to thoroughly reason about their concurrent data structure to make sure that they've got every single little aspect of it right. So, but what can we do? This is C++ after all. We know what our users are like. If we offer them atomic shared pointer and we say, this is great, it's easy to use, you won't write memory bugs, oh, but you get less throughput. They go, oh, I don't want that. no, I don't want to use that. I want high throughput. I'll use hazard pointers, right? I'm smart enough to do that. I'll get it right, trust me. But for non-experts, this is rarely the case. These things are tricky, but we know our users. This is C++. People want to squeeze out every bit of performance they can get, and so they will shoot themselves in the foot doing so. But it really seems like we kind of need deferred reclamation to get this high throughput. So can we somehow combine the two? Can we get deferred reclamation and RAII-based ownership? Now, if you're up to date with the latest concurrency TS and all of the latest fancy proposals, you may be thinking, hang on, I've heard of this. This has been proposed, right? It's called Cell, or maybe it's called Latest, or AKA Snapshot Source, or the type whose name changes every time I read the proposal for some reason. But it's, this data structure, it has been proposed. You can go read the proposal. And it supports this API. It manages a unique pointer. Okay, so it holds some unique resource, and it allows you to give it a new resource via a unique pointer and say, I'd like you to replace the current one with this. It also has a compare and swap-like operation called try update, which says, hey, I think this is what's currently stored in the cell. Replace it with this if I'm right. But then it has this extra magic operation called get snapshot. So what does this do? Well, how would we read from an API that atomically holds a shared pointer? It's not like we can load from it in the sense of an atomic, because that would have to copy, and we can't copy a unique pointer, right? So we can't copy out the unique pointer if we want to read it. Instead, what snapshot does, snapshot pointer says, here is an RAII type that will allow you to read this resource, and I guarantee that while you hold this snapshot, I promise you I won't delete it. So you can use this thing to read, but without actually taking over ownership. Okay, you don't have to take the unique pointer and become the owner and rip it away from everyone else who might want to use it. So this is a really good idea. But it is slightly limited because, well, we're limited to unique ownership. We can only use this with unique pointer. So this isn't general enough to support, the wide range of concurrent data structures that we might want to implement, which generally seem to require shared ownership. So what if we took this idea and combined it with atomic shared pointer? What if we had some type that could give us deferred reclamation and shared ownership with RAII-based ownership? So we could have an API that looks like this. We can store a shared pointer. We can load from the shared pointer. Right now we can load because we can take a copy of the shared pointer and increment the ref count. We can do a compare and swap like operation. So that's just atomic shared pointer, by the way. The first 3 lines, I haven't done anything new yet. But what is new and exciting here is this idea of what if we could put that get snapshot operation in a type like atomic shared pointer? Which is to say, I would like to read the object currently stored in this atomic shared pointer, but I don't want to become an owner. I don't want to increment the ref count because that's expensive. Could you please let me read it just without being an owner and promise me you won't delete it? I mean, that sounds like a big ask. It sounds like it's too good to be true. But I claim that we can do it. So the idea is it's like combining atomic shared pointer plus snapshot pointer. And the key fundamental idea is that get snapshot is going to allow us to read the managed object and be promised that, hey, I promise you I'm not going to delete it while you're reading it, but also you don't need to own a copy of the reference count, right? I will manage its lifetime for you. I will keep it safe. This sounds a bit too good to be true, but I'll hopefully convince you in a moment that this is possible. Let's have a look at, what advantages does this give us? How does this make it easier to write code? So I'm going to use an example of a single writer linked list that I've borrowed from Maged from his hazard pointers talk. So here is a single writer linked list, which means single writer means only one thread can do updates at a time, but all the other threads can do reads concurrently. So what we're looking at here is the remove operation, which, as you can see from the diagram here, takes some node called target and wants to delete it from the data structure. And it'll do that by swinging the next pointer of prev over to next. So on the left, we have the code using hazard pointers, and on the right, we have the code using this newly proposed type, which I'm going to, for now, call deferred shared pointer. I'll happily take suggestions for better names, but this is what I've come up with so far. So what's the difference here? Well, on the left, we have to call retire. We don't have to do that in the version on the right. Maybe that doesn't sound too bad. We also have to null out the next pointer after we swing across prev and splice target out of the data structure. It's not clear why we have to do that. If I didn't show you that, and I just showed you this code without that line, you'd probably believe me that it was correct. It's very subtle as to why that line of code has to be there. And if you don't have it, your data structure will be wrong and you might crash or return the wrong answer. The only line that we have in common is this single line here where we swing across the pointer, right? We store into prev's next pointer target's next pointer, which has the effect in this diagram here of splicing out target. Now, like I said, maybe this doesn't sound like it's too much more work. Like it's only 2 more lines, but those lines are subtle. If I didn't tell you, you might not believe me. We need to null out the next pointer. And it turns out that you have to do those 2 lines in that order, right? We are swinging the next pointer of prev, and then we are nulling out target's next pointer. In a completely sequential data structure, those could clearly be in either order. In a concurrent data structure, the order, the way they interleave, is very important. If you swapped those lines, it would be wrong. And it's so hard to reason about why that is the case. Had a question?
Yeah, is that because of the order in which the elements are retired in the end?
So the question was, is this because of the order in which the elements are retired? It basically has something to do with the fact that someone could come and delete 2 adjacent elements and like retire them both while you're reading one of them. Yes, the full details would not fit in this talk, but yes, that's roughly the idea. And it's really subtle to reason about why this is the correct code to write. And I don't want to have to teach beginners to do that reasoning. I would like to teach my students the code on the right, because it's basically the same as the sequential code, right? No fancy reasoning needed. Now, this was only the remove operation, right? We're not done yet. We also have to do the find operation that lets us search the data structure. So what does that look like? It's a bit more complicated. So what's going on here? I really couldn't explain this entire algorithm and all of its subtleties in this talk, but I will try and point out some of the pitfalls, some of the things that can go wrong. First of all, I've been mentioning that hazard pointers will often require the users to have a retry loop where they have to restart the operation if something happens, if something gets yoinked out from underneath them. So I'll try and explain this with a diagram. So we have a linked list. Someone wants to come along and read the linked list. Okay, great, they're happy, they're traversing along. And now another thread comes in and says, I'm going to delete that. And now the thread is not very happy. What does it do? In this situation with hazard pointers, the thread has no option but to restart. And that is what these lines of code are doing. But again, this is very subtle. You'll have to notice that there's not just one condition we check to restart, there's 2 of them. There are 2 breaks. If we only did one of them, if we forgot one of them, that would be bad. If we put them in the wrong order, that would be bad. Also notice this line in between them where we load the next pointer. That has to be between them. If you move that to a line before or after, that would also be bad, and this would also crash. So these 2 breaks are checking for 2 different things. One of them, the first one, is basically saying, I have to make sure I'm not about to read garbage that's already been deleted. The second one is more subtle. That second break is making sure you don't accidentally think you're at the end of the linked list because you saw a null next pointer, when you are in fact in this scenario where someone has actually just yoinked the node out, and that's why it has a null next pointer. So you need both of these if you want your operation to be correct. But it's very hard to reason about that and convince yourself that this is correct. I believe this is correct because I trust Meged to use hazard pointers correctly, but I don't trust non-experts to write this sort of code. So that's what I think is the trickiest part of this code. We would have to go back to the start of the linked list if we encounter either of these scenarios. But that's not the only thing. There's other things that can go wrong too. In the talk on Monday, Meged gave some examples of how you can get this line wrong too. It's very easy to mess up your pair of hazard pointers and use the wrong one or accidentally empty one of them and then try to use it again. I won't repeat those examples, but needless to say, there are even more bugs you can write that are very subtle and will appear to work, right? These will crash in production one day when, some evil race condition occurs. So I'd much rather write the code on the right. What does it do? It just traverses through the list. It checks, okay, if I don't have a node, I must have reached the end. So I didn't find what I was looking for. Otherwise, if I found the value I was looking for, great, return true. Otherwise, keep looking. Let's go to the next node. And again, that's as simple as the sequential code. If you were writing a non-concurrent linked list, it would look just like that, but without the atomic and get snapshot. But the actual instructions you'd be writing would look basically exactly the same. So this is nice and something that we can teach to beginners. I'd much rather teach beginners who are learning about concurrency to write the code on the right than to try and teach them to write the code on the left, because I don't even know if I can write the code on the left. It's extremely subtle and tricky, and instead, we can just write this. So, okay, it's a nice interface, but maybe it's just as slow as atomic shared pointer. I have to convince you that we can actually do this in a way that is efficient, right? So can we implement this efficiently? Well, we have some research that suggests yes, and if you want the full details, you can go and read these, or you can see our reference implementation on GitHub. Please go have a look at it. It could use some more stars. Disclaimer, this is not standard library quality code. This is still a research prototype, but it does work. And now you're probably asking or thinking, I don't want to read academic papers and I don't want to go trawling through your GitHub code. Just tell me how it works. Okay, I will tell you. I will give you the high-level overview because I can't give you all of the fine details in the span of this talk, but I will give you a high-level overview of what's going on. So if you want the full details, read the papers, or talk to me. Hell, I'd love to tell you about it. That would be nice. So the key idea, I'm going to give you the key to the mint here. How do we do this? We can repurpose deferred reclamation to defer something else. We're used to deferred reclamation, right, as, well, it defers reclamation. Yeah, that's what it's called. But who says it has to be used only to defer deleting objects, right? So usually deferred reclamation is about managing lifetime. It says, I want to defer deleting this thing to extend its lifetime. What if instead we repurposed that and used deferred reclamation to manage the reference count of the object instead? What does that mean? What does that look like? Well, basically it means we want to use deferred reclamation not to defer deleting an object, but to defer decrements to its reference count. So what would this look like? Well, I'm going to show you. Let's take our API from hazard pointers and RCU again. Usually, protect X means, hello, I'm about to read X. Please don't delete it from me. And retire X means I'm done with X. I've ripped it out of the data structure. I'd like to delete it, but only once people are done reading it. We could reimagine this now as protect X meaning, hello, I'm about to read X. So please don't decrement its reference count as part of an atomic operation while I'm reading it. And retire X is meaning I'm done with my copy of X with my reference, so I'd like to throw away my reference count, but don't do it if someone's currently protecting it. You might do it later. And this is implementable using hazard pointers and RCU. And note that this is stronger than just protecting the object from being deleted, because if I'm essentially protecting the reference count, if I'm saying you cannot decrement the reference count, well, I'm also protecting the object from being deleted, because if you can't decrement the reference count, in particular, you cannot get it to 0, which is what causes it to be deleted. But this subtle change turns out to be everything you need to implement a smart pointer with deferred reclamation, or specifically a shared pointer with deferred reclamation. So let's have a look at an implementation. This is slide code, so it's not precisely real code, but it should give you the idea. So we're going to have some atomic control block pointer like we would have in an atomic shared pointer. Well, let's look at some operations. So how would we load from this thing? How many slides of code do you think this will take? What if I told you 2 or 3 lines? That's pretty good. So to load, well, all we're going to do is we're going to say, I want to protect that pointer, which again, as I said, means please prevent anyone from decrementing this reference count as part of an atomic operation. Okay, I've succeeded in protecting it. That means I can safely increment the reference count because no one's going to drop it to 0, right, and mess me up. So I can increment it, and then I can return a shared pointer that manages this control block. Okay? And all we needed, right, was this magical protect operation, which says, hey, don't decrement the ref count while I'm doing this. Okay, that's load. What about store? Okay, store's got to be more complicated. If load was only 3 lines, store must be where the complexity is. No, we can do that in a few lines as well. Okay, we take in our desired shared pointer. We release it from desired, which just means I am basically nulling out desired because I want to move from it. I don't want the user to still have it at the end. So we're going to release from desired. We're going to just exchange desired into the atomic. And then the thing we got out of the atomic, we just replaced that. So we have to decrement its reference count. And we do so using retire because we want to say, hey, I'm done with this reference. Let's decrement the reference count. But if someone's protecting it, hold off and decrement it later. That's okay. And that's all we need to do. It's similarly not too hard to implement a compare exchange. It's about as simple as it could get, right? We're going to take our control block pointers from expected and desired. We're going to do a compare exchange on our underlying stat atomic. If it succeeds, then that means we have overwritten expected and therefore we've dropped its reference count by 1. So we retire it. We say, hey, we dropped the reference count by 1, so go and throw away my reference, but if someone's reading it, don't do it yet. You can defer that reference count decrement, that's fine. Otherwise, if we fail the CAS, we just do a load into expected because that's the semantics we expect from a compare exchange. Okay, so I've showed you the basic operations. These are the ones that atomic shared pointer already supports. What about that magical get snapshot operation? That was the whole point of this, right? Surely that must take a lot of lines of code. I don't really have enough space on my slide to put that, do I? No, I can fit it. It's just 2 lines. It's really just making heavy use of this magical protect operation. Get snapshot just says, okay, protect this pointer. Don't let people decrement the reference count on me, which means if no one can decrement the reference count, they can't delete it. So it's safe for me to hand this out to the user and tell them, yeah, you can use this. And we're just going to move this protection into our snapshot pointer. So I'm imagining here, I'm hand waving the code here. I'm imagining the protect is returning some kind of RAII handle around the protection. Like maybe it's returning a hazard pointer, and then I'm putting that in the snapshot pointer so that when the user gets rid of the snapshot, they will get rid of the hazard pointer or RCU reader, whatever it is, and then it will allow reclamation to proceed. So I've just fit the whole API on one slide. That's pretty nice. Okay, you probably still have one burning question left, which is okay, but really, is it actually fast? I mean, I've been hyping it up and telling you this is going to be fast, right? We're trying to match the performance of hazard pointers and RCU, but have we succeeded, right? Does this API really deliver what I've been promising? So let's go back to our performance test. We have our baseline, our unfortunate atomic shared pointer, and our high performance hazard pointers and RCU. So let's say we implement our smart pointer with deferred reclamation. And we can do that either with hazard pointers or RCU as the backend for that deferred reclamation. That's nice. So we can try out multiple variants of this. Let's see what happens if we implement our deferred shared pointer with hazard pointers as the backend. And we're almost on par with hazard pointers. We're just a hair behind the performance of hazard pointers, but with an interface that is completely encapsulated by RAII-based ownership. It's as easy to use as the unfortunate red line at the bottom, but we get performance that is competitive with hazard pointers. And like I said, we don't have to use hazard pointers. What if we say, no, I want more performance. I want even more. I want RCU-like performance. Okay, we can use RCU as the backend to power the deferred reclamation of our smart pointer. And it's basically on par with RCU. So that's pretty amazing. We're getting the performance of RCU and hazard pointers, but we now have a smart pointer type that is substantially easier for users to use, and it's something that beginners could could reasonably try and use in their code. Okay, so to wrap up, just some other final remarks that will be of interest to those of you who like atomic smart pointers. If you went to Timur's talk, you'll know that there's a common trade-off that people choose between when implementing atomic shared pointers. They either resort to using a double width CAS or this pointer packing approach where they steal, the top 16 bits of your pointer and use that to store a split reference count. This implementation requires neither. It's a single word CAS, and there's no bit stealing or pointer packing required. And that's good for multiple reasons. The most obvious one is portability. Hey, what if one day we don't have 16 bits of unused pointer? But portability is not the only advantage. It turns out that to implement some complicated concurrent data structures, you actually need to save some unused bits of the pointer and use those to store information about the data structure. So the concurrent BST I've been using as a running example is one such example. It actually needs to, as part of its operation, store some flags in the unused bits of the pointer as part of its deletion algorithm. Essentially, these flags are its way of communicating with other possible writers, hey, I'm deleting this, and making sure that concurrent writers all sync up correctly. So the user code might need these unused bits in their algorithm. So if we steal them from them, the user can't use these bits and then they can't implement these algorithms. But for this implementation, we do not need to do that. So we can expose these unused bits to the user in a safe API, of course. We're not going to give them the raw pointer, but we can give a safe API like set flag, get flag that gives them access to these unused bits. And now users can implement any data structure that they could implement with raw pointers. And one other nice fact, we also support weak pointers. I don't have time to talk about that in this talk, but you can use these ideas from this talk to get weak pointers as well. Now, there's still some to-dos. I'm taking, suggestions for a better name than deferred shared pointer, but it's okay. If cell is any indication, we can change it 10 times before it sees the light of day anyway, so that's okay. It would be nice to have a production quality implementation one day. What we have now is a research prototype. It would be nice to see if we can get this, a production quality level and get it used. Maybe get some users to test it out in their actual code. And if we can make it through all that, if we can come up with a good name and we can come up with a good implementation, maybe one day we can propose it for the concurrency TS or for the standard. So, okay, to wrap up, what was our goal? We wanted to know, can we get the best of both worlds? We were looking at atomic shared pointers and we said, oh, they're so nice, they're easy to use, but they're not very fast. And hazard pointers and RCU, well, they're great, high performance, but pretty tricky and easy for the user to mess up. Can we get the best of both worlds? And I hope that in this talk I've managed to convince you that the answer is yes. So thank you very much.
So well yet because first time I heard about them, but comparing us, you and the atomic shared pointers, I have the feeling that it's not fair because we don't look at how long it takes for memory to be actually deleted. In fact, I have the feeling if you do this RCU, isn't it the case that because you use so many threads that are all reading, that you're basically just starving out all the deletions, and then in the end nothing is ever deleted, and then obviously it's as fast as the baseline, or it's easy to think that it's as fast as the baseline because we don't delete.
Okay, so the question was a long question, but if I understand it, basically how do we expect the RCU implementation to not essentially run out of memory because we have so many readers and we're holding on to so many things? That's a concern with RCU, but that's not specifically a concern of this new type I'm proposing. That's already a concern of RCU. And RCU is widely used because if you use it in the right way, you won't starve yourself and run out of memory. But yes, you have to be careful when using RCU. And in the same vein, if you wanted to use the new RCU-powered smart pointer, you would need the same considerations of, okay, I better not hold on to this read lock for too long or I'll run out of memory. So yes, that is a concern, but it's not particularly a concern that is due to this new algorithm, that's already something you have to think about with RCU. So hazard pointers are generally the safer option in that regard, but they're harder to actually reason about when you put them in your data structure. So if you're using the smart pointer type, the best thing to do would be to use the hazard pointer backed smart pointer here. And then you don't have to worry about that, but you also don't have to worry about the usual complexities of hazard pointers. So yeah, you should be careful with the RCU version in the same way that you would be careful with regular RCU. So yes.
Does your implementation support shared pointer aliasing?
The question was, does our implementation support shared pointer aliasing?
This is malfunction.
No, not yet. Maybe one day. Because this is a new type we're proposing, it's not atomic shared pointer, we could decide to support aliasing or not. And that's, that's up to us to figure out if we want to propose this for the TS or the standard. Like, should we support aliasing? If you saw Tim Er's talk, you'll know that actually doing aliasing is one of the tricky parts of getting everything to work and still be lock-free. So at the moment, no, we don't do aliasing, but we could reasonably add it using the same techniques that Tim Er discussed in his talk for adding aliasing to atomic shared pointers.
Thanks for the talk. I wanted to know what happens if you shift the readers-writers ratio. So right now you have mostly readers, which is a fair assumption in most use cases. But what happens if you have more writers?
Okay, good question. So the question was, what happens if we have more writers? Because right now we're doing 99% reads, 1% updates. And this is pretty typical for deferred reclamation techniques like hazard pointers and RCU. They are mostly designed for cases where there are mostly readers. But, well, let's have a look. I do have a slide for that. I'm prepared for this. So if we do 10% updates, we can see that the throughput goes down. We get a little bit more of a gap between the smart pointer version and the non-smart pointer version, but we still get scaling. So it's not too bad. In general, the advice is if you have really heavy updates, like 50%, then you should probably not use these sorts of techniques. Something very fun happens in the 50% updates case, though. You might notice, what on earth's happening to the baseline? It's falling over. Well, we're doing so many updates, their allocator is really mad at us because we're never deleting anything. So actually the baseline falls over when you do too many updates. But this can also be explained by your cache, right? When you start doing so many updates, you're also not having very much in cache anymore because there's constantly new nodes being added that you don't have in your cache compared to last time. So the answer is yes, you can see some interesting performance if you look at different workloads. Generally speaking, these data structures are designed for low update rates, but they still work. So yeah, you can also look at like a bigger tree as well. I have a graph for that. You'll notice that if I make the tree huge, 100 million instead of 100,000, all of the algorithms sort of converge to the same performance, except atomic shared pointer, of course. But the others all pretty much converge, and the reason for that is because now the tree is so big it doesn't fit in cache, the overhead of your memory management becomes barely noticeable. So yeah, it's good to look at different workloads as well. So good question, and I was ready for it because it is a very important question that we should benchmark on different workloads as well.
Yeah, thanks for the talk. That was awesome. Could you go to slide 44, please?
Sure.
Yeah.
Here.
So when we look at this, do I understand it correctly? Just a clarification question. Your snapshot shared pointer is basically a superset of the atomic shared pointer in terms of API.
Right.
So basically that this get snapshot thing is kind of an additional thing that you can use for certain data structures, but that this benchmark actually you only use the set of the API that it shares with atomic shared pointer. So it's like a one-to-one comparison basically of implementing different ways of implementing atomic shared pointer. Did I get that right, or am I confused?
Roughly. So the question was, so we basically have a superset of the API of atomic shared pointer, which is right. We have store, load, cas, and this new operation get snapshot. Now, the difference here is that in this benchmark, the smart pointers that have get snapshot are using it. The atomic shared pointer is doing load because it doesn't have a get snapshot method. So we're not necessarily using the same API for atomic shared pointer and the new smart pointer, because the point is we're sort of seeing how much better can we do if we add a new operation that atomic smart pointer doesn't have. Great. All right, and I think we're out of time. Sorry, I didn't quite hear the question. The top 3 what of atomic shared pointers? Oh, so the question was, what are the other implementations of atomic shared pointer? Because I mentioned I know about 5 of them. Most of them are mentioned in Timo's talk. There's Facebook's Folly implementation. There's Anthony Williams' implementation in his commercial Just Thread library. There's several that my research group has written. And there's also some other research ones in the academic literature as well, which you'll find pointers to those. If you read my paper, you'll find pointers to all of those other ones. So that is all we have for today. Thank you very much, everyone.